Today in physics we'll be talking about the Atwood machine under the effects of friction. This is part 5. So we have a cylinder. On top of the cylinder, we have a massless string. On the left side of the string, we have weight A of mass ma, and on the right side of the string, we have weight B of mass mb, where mb is less than ma. Now B starts off at some height, at some point O, and we also give B an initial velocity which we'll call V0. Now we're asked to find the ratio ma over mb in order for B, once we give it an initial velocity, for it to keep going downwards until it reaches a certain point. And once it reaches that certain point, it turns around and starts moving upward instead. And once it starts moving upwards, eventually it passes point O, the original point again, and then it keeps going upwards. So we're asked to find what's the minimum ratio that MA over MB has to be in order for this to happen. Additionally, we have a coefficient of static friction, which I'll call mu0, that is equal to 1.0. And there's also a coefficient of kinetic friction called mu, which is less than the coefficient of static friction, so it's less than 1.0. One way to think about this is, let's say A and B are already at equilibrium, so B is just enough so that if we just leave it there and we just leave A there, they will balance each other out since friction will help B, since we know that the mass of B is smaller than the mass of A. Then, once we give B an initial velocity, perhaps B will just keep going on down and will keep accelerating downwards instead of turning around at its lowest point, since the ratio, the difference between mass A and mass B, might not be large enough to affect B to have it turn around and start accelerating upwards instead. So let's think back to part 4, where we figured out a relationship between two masses, one larger than the other, where big M is smaller than small m. We figured out a relationship between the two when the number of turns of the string around the cylinder is equal to 0. Namely, large M is equal to small m times e to the mu0 pi. So this is the minimum amount that large M has to be in order to have small m remain at rest. So this is also the minimum amount that small m has to be if we solve for small m in order to have large m remain at rest. So this is what allows the system to remain at rest. Now, if we think about it, if we give small m of initial velocity, however, that might push the system out of equilibrium and have it start moving, so have it out of rest. And if we want m to come back and start moving upwards instead of continually moving downwards, then we probably want large m to be larger. So we should say something along the lines of large m is greater than small m times e to the mu0 pi. Now if we look at our own problem with MA and MB, we can see that if we just leave the system to itself and we don't have a weight B there initially, then the system is going to want to start rotating counterclockwise downward to the left, following the effects of gravity upon weight A. But once we put weight B there, and if we don't give weight B an initial velocity, then we see that then the system becomes balanced. It's similar to the idea where we had large M there initially, and in order to have the system not rotate counterclockwise following the effects of gravity on large M, we put in a small m here. But since we've also given weight B here, in our case for problem 5, we've given weight B here an actual initial velocity. We want ma to be larger in order to counteract the effects of the kinetic energy, initial kinetic energy, which we're giving to weight B. So we can replace large m and small m, which is a general relationship to ma is larger than mb times e to the mu0 pi. Or in this case, mu0, as we mentioned before, is a coefficient of static friction. So once we have that, then we can find the ratio of the two masses by dividing. So we have ma over mb is larger than e to the mu 0 pi. In our case, mu 0 is 1.0, so e to the mu 0 pi is simply equal to e to the pi, and that is approximately equal to 23. So we find that the minimum value of ma over mb, in order for b to turn back and start moving upwards again once we give it an initial velocity, is approximately 23, namely e to the pi.